Okay. Did you guys see a pump up showing the recording is ongoing? Okay, great.
Yes.
Oh,
We did.
okay, Björn, take it away.
Okay. This presentation should be about 20 minutes long, and then afterwards we have a 20-minute question and discussion session. And please feel free, because we're just 10 people, to just interrupt me during the presentation. We can also divert it a little bit and go into deeper discussion and then see where the flow takes us. So this presentation is about how to build fast emulators in climate models. And the big framework is the question whether we can find a very fast mapping from climate policy scenarios, such as what if we increase the carbon tax by a little, all the way through the pipeline of models to local climate impacts. So here, for example, you can see a visualization of a flooded scene. This project is part of one of the MIT Climate Grant Challenges, which is called Bringing Computation to the Climate Challenge. And I'm advised by Noel Zelin and Rafael Ferrari. Okay, there we go. So some of you might be aware that climate models are very expensive to run because they have so many components. And because of so for example, a couple of years ago, Fuhrer et al. Tried to run a climate model at 2-kilometer resolution, and then just simulating one simulation year took them 3 weeks on a 4,000 GPU node supercomputer, consumed the same electricity a coal power plant would have generated in an hour. So clearly that's too expensive for rapid exploration of what our futures could be like. So we think very carefully about which policy scenarios do we want to run our climate models on. So as a solution, people have been developing emulators. Emulators are these very fast approximations, these fast surrogates or reduced order models that approximate the underlying dynamics. So here you can see an emulator developed by collaborators called En-ROADS, and it lets us quickly explore climate policies such as what is the impact of reducing deforestation about 100 years down the line on global temperature increase. These models are really nice because they run so fast, which makes them very accessible. And this model has been used by over 200,000 people over the world, primarily as an education and exercise. But what it cannot do is show you local impacts. So the only thing you can see here is a purely global model. It tells us about the global temperature increase, whereas the local temperature increase can vary significantly, for example, in the Arctic versus New England, Europe. So the question becomes, how can we emulate the effects of climate policies on the local climate impacts? And that's what we've been working on in this Climate Grant Challenge, where we are revisioning a toolbox that comes out of this with some fundamental questions, with some fundamental science along the way, where we have some sliders, such as deforestation and carbon tax, and then can see very local impacts. So to disentangle such an emulator, there's a lot of steps that the emulator has to take along the way. So what we've seen here is these sliders. These sliders define climate policies. The climate policies feed into an energy policy model or an integrated assessment model that spits out CO2 emission trajectories over time. The CO2 or methane, sulfur dioxide, black carbon trajectories over time are fed into Earth system models that integrate the dynamics at a low resolution, 50 to 100 kilometer over time. The low resolution climate projections, which are now states of the climate, so temperature, humidity, pressure, wind variables, are downscaled onto a higher resolution grid, fed into impact models, which in this case is a model, which in this case was the climate state being fed into a hurricane track model, which fed into a flood model, a storm surge model. And now you can see the storm surge in Houston, and that was fed into a visualization. So my work thinks about, along this vertical, how can we integrate machine learning to speed up each component in here, Today, we're going to focus specifically on speeding up the component of the dynamic core of the climate model. So we call this climate emulation. Specifically in climate emulation, then the goal becomes, can we reduce inference time while maintaining a specified amount of accuracy by approximating the climate model with machine learning? In general, the pipeline to do that would be, first we generate a large data set using a supercomputer. So that means specifying initial conditions, forcings and parameters, boundary conditions, sort of varying with some defined distribution over those initial conditions, parameters, and boundary conditions, generating solutions. So in this case, for example, led by the postdoc who's sitting next to me, we generated a large data set of a simplified ocean simulation using the MIT GCM climate model. Then given this very large data set, we have to decide which aspect, with which relationship within this data set do we want machine learning to approximate. So we pick some form of inputs and we map them to targets. In this case, the input was the state at time t, and the output was the state of the whole simulation, the next time step. Once the machine learning model is trained, we hope that it can run fast inference. In this case, there was a slight drop in accuracy, but therefore we gained a runtime increase of 600 times faster model, which was primarily done due to the larger time step that the machine learning model was able to give us. So in this emulation, there is now becoming more and more attention from Google, IBM, NVIDIA, Microsoft, that all have their climate teams thinking about whether data and deep learning can help, and they're developing the biggest models on it. They're partially interested in this because climate emulation does pose very new challenges in deep learning. For example, it's a very high-dimensional task. The first ChatGPT, the ChatGPT-3 was trained on 570 gigabyte of data, whereas just one data set from the Earth Sciences, the CMIP6 data set, which contains climate simulations, is 20 petabytes large. It's a risk-sensitive application. When ChatGPT predicts a text that's slightly wrong, usually that's okay. If we predict climate, if we do climate predictions that are overconfident, show too much temperature increase, then I think people would question the climate science and lose trust. It's a long-term time series problem. The deep learning world in NeurIPS, there's a benchmark data set called the Long Range Arena, which asks machine learning models to forecast 10,000 time steps ahead. And it's usually cited as that's the longest forecasting step here. Whereas if you were to emulate a climate model autoregressively, we're talking about 1 million steps that need to be forecasted in time. Lastly, that all sounds kind of infeasible to deep learning the state it is right now. So what they're also interested is combining current science from deep learning with physical constraints. So the second part, so this was an overview of our work, and now I want to dive into one work in a bit more detail, which we call a cautionary tale about deep learning-based climate emulators, which, back to our overview graphic, asks the question, given cumulative CO2 emission trajectories, can we map them onto temperature impacts? And I'll go into the setting in more detail, but after this, you can also find all of the code published at this link in a hopefully accessible manner. So there is, in climate emulation, I think there's 2 benchmark data sets. A benchmark data set is very useful because once it is open sourced, it kind of defines for the subfield how one could set up the input-output learning relationship, and then makes it very transparent to develop multiple machine learning approaches and see which machine learning approach is the best. So in climate emulation, Duncan Watson Paris published Climate Bench 2 years ago, and they set up the task as follows. They set up the task where they have a black carbon and a sulfur dioxide map over the globe, and a globally averaged cumulative CO2 emissions from anthropogenic sources and a globally averaged methane source. And those inputs are given for 10 years in a row. So each of those years is annually averaged as well. So now we have 2 global maps and 2 global inputs multiplied over 10 time steps. And they used this as input to various machine learning architectures, and the target was to predict a temperature map, or a map of some climate variable, specifically temperature, diurnal temperature range, precipitation, and extreme precipitation. And then this model is trained on, so going back here again, I'm plotting the cumulative CO2 emissions over time, so just one of the input variables. And you can see here, there's 5 different scenarios. These are the socioeconomic pathways that are used in CMIP6. These are the outputs of the integrated assessment model, the CO2 trajectories over time. And we use 4 of those as during the training data set, and 1 in the middle we use for validation and test. So there's no held out test data set, the validation and the test is the same. So that held out test data set. They proceeded to train a CNN LSTM, was the best model on this benchmark. So that's a convolutional neural network combined with an LSTM, a long short-term memory network. And we can see here that the target temperatures averaged over 2080 to 2100, and the predicted temperatures, they look very similar. Both of those show sort of patterns that expect the climate, the North Atlantic warming hole, Arctic amplification, a warmer northern than the southern hemisphere. Sorry, the other way. And the root mean square error of that is really nicely done in the data in the benchmark data set. We now have a single metric that can tell us which model is the best. So in this case, the model was 0.107. Then Microsoft heard of this, and they built an even deeper learning approach. So now we're going from 1 million to, I think, 100 million parameters. And this model is called ClimaX, and it uses vision transformers, which have become one of the state-of-the-art models. Published in this paper, Attention is All You Need. I think the paper was published in 2017, and by now it has about, how many? 10,000 citations. And so hugely impactful paper. So this paper now then became state-of-the-art on Climate Bench, even when the model was only trained using a maximum of 80 NVIDIA V100 GPUs, whereas 1 NVIDIA V100 is approximately the same as 8 desktop GPUs. So you get an idea of the scale of the compute that is now being used for the climate emulation task. It did reduce the root mean squared error. So what we did in our analysis is we took some step backs and developed a linear regression model that's also called or referred to as linear pattern scaling, and I think was developed first in the 1990s. So the idea here is we only take a single of all the available inputs. They are global cumulative CO2 emissions. We fit a linear regression model that maps that onto global temperature anomalies. And then we fit 1 linear regression model per grid cell that maps the global temperature onto the local temperature map. And then we can produce the same test set. It's now, and then we can evaluate this model on the same test set. And we can see that this linear pattern scaling model has almost the same patterns as the ground truth. And if we calculate that error, the linear pattern scaling actually has a lower error than the ClimaX model. We proceed to compare this linear pattern scaling. I couldn't actually believe that it's that good, but the linear pattern scaling on the other variables of the data set, which are the surface air temperature, that's what I showed you right now, but there's also diurnal temperature range, precipitation, and 90th percentile precipitation. And the linear pattern scaling outperforms all deep learning models in the spatial precipitation the spatial 90th percentile precipitation, and the spatial surface air temperature. So overall, we've seen that the linear pattern scaling model is better than these neural network-based models for predicting spatial patterns. For predicting global patterns, for the distinction here is what you can see in this table is there's a column for spatial and there's a column for global error. The spatial error is calculated by calculating the error per grid cell first and then averaging, whereas the global error is calculated by averaging and then calculating the error. So it evaluates the global bias. Overall, the linear pattern scaling model has a worse global bias than the neural networks models. And I'm still trying to find out why that is. That seems kind of curious. And then the diurnal temperature range was also a variable that seemed to be more complicated to predict. So why was linear pattern scaling so good? I think it brings us back to remembering that domain knowledge is so incredibly important. People have known for a long time that cumulative CO2 emissions relate almost linearly to the global temperature increase. So what you can see here is the cumulative emissions over time, and you can see them increasing. This is the inputs. And what you can see here is the target outputs, which is the surface temperature increasing over time for each of the scenarios. And then if we just create a scatter plot in between those two, then we can see the relationship in between those two is almost linear on the global scale. And on the local scale, a scatter plot of global over local temperatures is also almost linearly if plotted for a random selection of grid points. So where I kind of want to take this next is I think it would be really interesting in the climate emulation world where we find a way to communicate what are the easy to do challenges and what are the more harder to do challenges within this world of emulation, of emulating the climate system. For example, this table lets us suggest that there might be a lot of room for increasing nonlinearly models, might be a lot of room for machine learning in predicting diurnal temperature range. So to get to that state, we have to address one big thing, which is the internal variability. Right now, the data set contains data from one climate model that was run for 3 realizations. So one realization is that we slightly perturb the parameters of the climate model, the initial condition, and we run it over the full years, over the 250 years. And what I'm plotting now here is 4 plots for one plot for one region. And for example, in Greenland, Iceland region, you can see the temperatures plotted over the test set. So this is the SSP245 test set. And the global temperatures already fluctuate quite a little bit, even though it is an average over all the realizations in the data set. But then on the local temperatures, you can see even stronger how much the temperatures fluctuate through each year. And that is expected if we just have one climate model, because the climate system naturally fluctuates every year to the other, having stronger temperatures, higher and lower temperatures. But that washes out the quality of our benchmark data set, because it is now really hard to say whether the increase in accuracy is due to a model improvement or due to just internal variability. So what I want to do next is repeat this exercise with a data set that we will need to collect ourselves that contains a lot more ensemble members than 3. Going back full circle to the idea that we want to have an app that lets us explore sliders, and you can see the temperature, the climate impacts in real time. We have been working on a web app that I think is currently down, but when it's not down, you can see it in this QR link. And if you do want to reproduce the results that we've done, you can see them at this tutorial. Okay, that was it. Thank you so much for listening, and we can go on to questions now.
Hi. So thank you very much, Björn. That was really nice. I guess my question, well, I have two quick questions. So the first one is, I think like in the latest round of NeurIPS, there seems to be quite a lot of the climate benchmark data sets that came out. So ClimSim and Climate Set as well. I don't know if are those suitable for what you want to do, or is it that you want more ensemble members still from NOR ESM, or do you want to go across climate models? Because I think that's the aim of the climate set one is
Right.
to different models.
Yeah, so ClimSim was part of that paper. ClimSim is about using machine learning for learning parametrizations.
Okay.
So a slightly different goal where the idea is, where the end goal, I think, is to have, I think the end goal in climate parametrizations would be to have another model in CMIP7 that sort of competes with all the other models, but then says, we only need to run at a resolution of 100 kilometers, but we do actually feature the accuracy of a 1 kilometer model.
Yeah.
So that's a slightly different task. What we're interested in is sort of models that can run on the scale of fractions of a second instead of then still needing hours to run. So the climate set is the most related there, but climate set also unfortunately only contains one realization per model. So what climate set lets us explore is the variability in between models, but not the variability within, not the variability between years.
Okay, super. That makes sense. And then just briefly, the other one, as you said, like this pattern matching idea for temperature has been on for a long time, and it's really cool that you showed that it works, really nicely in this case. I was just wondering though, for precipitation, I wouldn't like intuitively expect that to work in the same way. I don't know. I couldn't quite see on your results whether it did or it didn't. But yeah.
Yeah, we can see that in precipitation, the error is the lowest among the models. But I think there's like the internal variability, which is here given as the standard deviation between three members. So it's not a very robust number, but it is a number that's almost on the same scale as the error. So while linear pattern scaling is better than the other models here, I think there's an argument that one could make that says all of these models are approximately the same quality. Yes. But then there's also the other argument that says that there is an almost linear relationship